Another thing that we can use integration for is to find what we call the arc length. So the length of an arc or the length of a curve of any kind. So this is kind of an interesting idea because, we typically are using integration to find area, right? And we wouldn't think of it as something that can be used really to find length. But it actually can be used that way. We just kind of have to be creative with it and how we come up with the formula. So let's just start by kind of reasoning through exactly what we would want to do. Okay. So say we have this, I guess we can call it not like a line segment, but a like a curve segment, right? This is what we call an arc. Just basically anything which has some kind of curve on it, right? Like this does at various points here. So we're going to start by thinking about how we could approximate this area, right? This is typically how we do things in calculus, right? We start with an approximation and then we work in some kind of limit so that we get an exact answer. So let's say that, let's use the idea of partitions like we used when we started developing the integral, right? So let's say we break it up into these. We're going to use these x values down here. Okay, we'll call this last one b and the first one a. And we have these outputs for each of these values, right? So f of x0 and f of x1. And what we're going to do is we're going to find the length of the line segment between these 2 points. Okay. So I'll use red here, I guess. So this is kind of like when we were trying to find the slope of the tangent line, and we started by finding the slope of the secant line. And then we move them closer and closer together. So same kind of idea here. We want to find the length of this line first, which is, of course, not the same length as the arc that it's next to. But, maybe if we did 2 segments in between these, like if we took the point exactly in the middle of these and then found the length of 2 segments, then it would be a better approximation, right? So that's kind of the idea here. So we're going to do this with all of these points here. Okay. So we're just going to keep drawing lines between these. Some of these will be better approximations than others. Like this part right here, it's relatively straight. So it's going to be a very good approximation of the actual arc length. Now, finding the distance between 2 points like this is a matter of just using the distance formula, right? So I'll go ahead and we'll kind of draw like imaginary lines here connecting the triangle here, right? But in general, this is going to be what we call the change in x, delta x, and this is going to be the change in y, delta y. And then from there, the length of this segment right here is going to be the square root of delta x squared plus delta y squared, right? And we'll do that for each segment. So delta x and delta y will be different depending on which segment we're looking at, of course, but this is the general formula. And this is just the distance formula, right? So I'll just write this down. We're using delta instead of, like the same notation we used when we derived it in Math Tools 1, if you were in that class, but delta is very common. The Greek letter delta, which just looks like a triangle, it's very common to use for any kind of change. As I think we talked about that with the derivatives at some point. So we want to focus on this quantity first of all. Okay, so let's go ahead. We'll come back to this. Let's just focus on this quantity first of all. We want to rewrite this a little bit. Okay, so we have delta x squared and delta y squared. And this gives us the length of each line segment. We can rewrite this a little bit. We'll factor out a delta x squared from both of these terms here. So this would be 1 plus delta y over delta x squared. So we're doing a little bit of force factoring here. And then this allows us to then pull out the delta x squared part because now it's being multiplied in there. Just make that clear that that's a 1 here. It's all kind of smushed together. So now we can pull that delta x out, right? We can take the square root of just that part because it's part of a product. So that's just one of the exponent rules. And then on the inside, we have 1 plus delta y over delta x squared. Okay. So now you might kind of get to, you might start to see where we're going with this, right? Delta y over delta x, that's the slope. So this means that we're looking to kind of introduce a derivative in here. Okay. So specifically by the mean value theorem, and you can check that we're meeting the conditions of the mean value theorem, which we are here. Remember, if we're talking about an arc, it has to be continuous, right? That's just kind of the definition of an arc. So we'll meet the conditions of the mean value theorem here. So by the mean value theorem, there exists a point xi, we'll call it xi star, in xi minus 1 to xi. Okay, so this is just the name of this interval, right? The interval between any two of these x's. We're happen to draw it on the first one, but we could do this between any of them. Then there exists a point xi star in there such that f prime of xi star is equal to delta y. We could say delta yi over delta x, right, to indicate that we are in that specific interval, right? Maybe we say delta xi. Okay, so this is just this is exactly what the mean value theorem says, that you take your change in y divided by your change in x, aka like the average rate of change or the slope, or however you're looking at it. And there is a point guaranteed by the mean value theorem that the derivative is the same at that point. So let's call this up here, let's call it L. We'll use a cursive L here. L, just so that we don't have to rewrite the whole thing. So L is equal to delta x times the square root of 1 plus f prime of xi star squared. Okay, so wherever this point is guaranteed by the mean value theorem, we're going to replace the slope with the derivative at that point. Okay, so this is only for one line segment, of course, so we still need to add all of the line segments together. So let's call this Li first of all, and we'll put the i's in there to indicate that this is only for one segment. Okay, so L would be the sum of I equals 1 to n of the Li's. Okay, so we add them all up, say that there's n of them, we add them all up, which is going to be the sum of I equals 1 to n of 1 plus f prime of xi star squared. Whoops. And then on the outside, we have times the delta xi. Okay. Now we don't really need to say delta xi because I didn't indicate it up here, but the we can take these to be equidistant, right? So we can say that these are all the same length, all of these x values here, okay? Or intervals, I should say, not the values themselves. So I guess we don't really need the xi's. It doesn't necessarily hurt because in this case, delta x is equal to delta xi because they're all the same length. But we don't have to write that. So not really that important, just kind of a notational thing here. So then, again, we can imagine just kind of like when we started doing this with the rectangles, when we were finding the area. Like I said, if we break this up into two, this segment right here, sorry, I don't think my cursor is coming up. I'm pointing, but anyway, the segment between f of x0 and f of x1, if we were to go ahead and split it into two segments and say then we had like this other x, I don't know, like x.5 or something like that, and we put that one in here, and then we looked at those segments, we can see that we start to get a better approximation, right? And we could do this with all of them. So basically, if we keep breaking this up into more and more segments, we're going to get a better and better approximation. So just like again with the rectangles, with the Riemann sums, what we want to do is then take the limit as n goes to infinity of the sum . Okay. So just copy everything down here. And then just like we already showed, you know, in the definition of the integral, this is equal exactly, this limit is equal to the integral from a to b, which remember that's what we called our first and last partitions, right? Of 1 plus f prime of x squared dx. Okay, so a lot is taken care of by that limit, right? The sum turns into an integral. The derivative, we no longer need a specific value there. We can just do the f prime of x, and the delta x becomes infinitesimally small into that dx quantity. Okay, so then we have a general formula for the arc length. Okay. So now we can use integrals to not only find area, not only volume, but also length. Okay. So let's go ahead and see this in action. Okay. So let's see, we can do, here, let's try, we're gonna let f of x be 2x to the 3 halves, and we want to calculate the arc length over 0, 1. Okay, so some of these can be deceptively tricky. Like if you just get something like x squared, for example, even just finding the arc length of that leaves you with an integral that's actually pretty hard to evaluate. Like that one in particular really leads to one where you kind of just have to use like a computer program to approximate it, or some kind of like table of integrals. So integrals in general, I mean, they can just kind of be deceptively tricky sometimes, even with simple functions, but this one just gets kind of weird because then you're also taking the derivative first and squaring it and then throwing it under the square root sign, and that square root sign can make things pretty tricky. So this one should be okay though, so let's try this one. So via this formula here, what we want to do is we want to find the integral from 0 to 1 of, maybe it's good actually to take the derivative first, just so I don't have to write it again. See, so we're going to need f prime here. So f prime of x is going to be 3/2 times 2x to the 1/2. Okay, so 3 x to the 1/2. At this point in the course, you probably are at the point where it's like, it's been so long since you've taken a derivative. I mean, it hasn't really been, but you know, we've been in like integral mode for so long. So when you start to like go back to derivatives for the first time, I know it can be kind of tricky to like kind of keep them straight. Like we'll often have the tendency to actually accidentally take the antiderivative. So just something to be careful of. You know, just take an extra second to think about, you know, taking the derivative versus the antiderivative. So anyway, so here we use the power rule, right? So we get 3x to the 1/2. And then we're going to end up squaring that too, right? So we can just go ahead and do that whole quantity. So 3x to the 1/2 squared is going to be just 9x. Okay, so that makes it a little bit easier to deal with. So the arc length then is going to be the integral from 0 to 1 of the square root of 1 plus 9x dx. Okay. So the square root in general can just make it tricky. Like if you have anything, any kind of polynomial higher than a first power, then these can be kind of tricky. You might need some kind of like trig substitution or something like that. Here we can just do a simple u substitution, right? So 1 plus 9x and then du is just 9. Okay, which implies that 1/9 du is equal to dx. So we'll make that substitution here. You can sub the bounds too if you want. So x equals 0 implies that u is equal to 1, and x equals 1 implies that u is equal to 10. So we'll just go ahead and change the bounds while we're at it. And then it's just a little easier. You don't have to sub back in at the end. So this is going to be 1/9 times the integral of the square root of u du. So 1/9 back to antiderivative mode now. So you'll get 2/3 u to the 3/2 from u equals 1 to u equals 10. Okay, so you can bring that 2/3 out. So this will be 2/27. And then we're going to get 10 to the 3/2 minus 1. Okay, and there's no good way to simplify this for like an exact answer. Best you could do would be, this would be 10 root 10. But that's about as best you can get. So you could throw it in a calculator. The approximation here should be 2.268. Okay, so that tells us the length of this arc.